Good morning, guys. Welcome to week 2 of online learning. This week we're going to keep talking about gas laws and calculations. So we're going to learn about 2 new laws and how to do their calculations. The first one we're dealing with is called Gay-Lussac's law, which deals with the relationship between pressure and temperature. So last week we talked about the relationship between temperature and pressure here. We said that as you increase the temperature of a gas, you're also going to increase the pressure, because as the temperature increases, your particles start to move faster, they start to collide more, and so you get an increased pressure. So we called that a direct relationship, because as one increases, so does the other. Here is the equation we're going to use. P1 over T1 equals P2 over T2. It looks really similar to one of the equations we used last week, just with different variables. So let's work a couple practice problems. The first one says if a gas is cooled from 315 Kelvin to 231 Kelvin and the volume is kept constant, meaning it doesn't change, we don't need to worry about it, what final pressure will result if the original pressure was 0.82 atmospheres? So the first thing I always like to do is write down all of your given information along with whatever variable it is. So I see 315 Kelvin, 231 Kelvin. That would be my initial temperature and my final temperature. So it says it is cooled from 315 Kelvin. So that's my T1. We start at 315. We cool it down to T2, which is 231 Kelvin. It says volume is kept constant. What final pressure, so that's what I'm looking for, will result if the original pressure was 0.82 atmospheres. So 0.82 is going to be my original pressure. And my final pressure, P2, that's what we're looking for here. Now, we just got to plug it in. So plug in to your equation, which is P1 over T1 equals P2 over T2. And then it's just algebra. So if we plug in, P1 is 0.82 atmospheres. My T1 is 315 Kelvin. P2, I don't know, that's what I'm looking for. T2 is 231 Kelvin. Then we just rearrange to solve. So I want to isolate my P2 over here by himself, so I'm going to get rid of this 231 Kelvin by multiplying both sides by 231. That gets rid of it over here. So if we rewrite that, it'll be 231 Kelvin times 0.82 atmospheres over 315 Kelvin is equal to my P2. Then you just plug it into the calculator. So 231 times 0.82 divided by 315 will get you about 0.60. The units here are atmospheres because we're talking pressure. You can double check that because Kelvin on top cancels Kelvin on bottom. You're left with just atmospheres. So my P2 here is 0.6 atmospheres. You can check to make sure that's a reasonable number because we know that our pressure and our temperature either increase or decrease together. So if we look over here, we decreased the temperature. We cooled it from 315 to 231. So our pressure should also go down, and it does. So we started at 0.82, we decreased to 0.60. So that's a reasonable answer. Okay, number 2. If a gas in a closed container is pressurized from 12 atmospheres to 25 atmospheres and its original temperature was 32 degrees Celsius, what would the final temperature of the gas be in Kelvin? Okay, so let's go through, write down all our information here. So I see that I started at 12 atmospheres and I increased it to 25. So atmosphere is a unit of pressure. So my P1 would be 12. Atmospheres is just ATM. P2 is 25 atmospheres. My original temperature, it says, was 32 degrees C. Okay, red flag here though. If you remember back to last week, I said that the temperature cannot be in degrees Celsius. We have to convert it into Kelvin. If we look back in our notes here, I said the way to do that conversion is all you do is you take your degrees Celsius, add 273, and that converts it into Kelvin. So all we have to do is add 273 to this number, which is going to get me 305 Kelvin. So it's a simple step, but it's very important. Your temperature must be in Kelvin for these calculations. Then it asks us what would be the final temperature. So that's what we're looking for here. Then again, we just plug it in. P1 over T1 equals P2 over T2. So my P1 here is 12 atmospheres. T1 is 305 Kelvin. Make sure you use the Kelvin value. P2 is 25 atmospheres. And T2 is my unknown. Now we just rearrange and solve. So the first thing I would do here is move my T2 from the bottom to the top. So in order to do that, I'm going to multiply both sides by T2, and I'm going to have to kind of squeeze it over here. Sorry. So T2 cancels over here. If we rewrite that, it's going to look like T2 on the left times 12 atmospheres over 305 Kelvin is equal to 25 atmospheres. Now to get T2 by itself, I'm going to multiply by the inverse of this. So I'm going to flip this and multiply it. So all I'm going to do once I do that is I'm going to have T2 over here on the left by himself is equal to 25 atmospheres times the inverse here. So I would have to multiply by 305 to get rid of it over here. So 305 comes over to the top. And to get rid of my 12 atmospheres on the left on top, I have to divide it over to the bottom. So 12 atmospheres here. My atmospheres cancel because I have one on top, one on bottom. And then I just multiply and divide. So 25 times 305 divided by 12 gets you a T2 of 635 Kelvin. Again, you should check yourself. If I look over here, my pressure increased from 12 to 25, so I would expect my temperature to also increase. So my original temperature was 305, it increased to 635, so that's a reasonable number. Okay, that's Gay-Lussac's law, so it's really similar to one of the laws we did last week, Charles's law, so not anything too crazy. The last law we're going to look at today is called Dalton's law of partial pressures. This one is really easy. So Dalton's law says that the total pressure of a gas is equal to the sum of all the partial pressures of all the gases. So all we're going to do is add together all the partial pressures to get a total pressure. That's it. It's pretty easy peasy. Y'all will like these calculations. They're not hard. So if we look at the problems, it says, number 1, 3 gases are combined in a tank at 25 degrees C. Oxygen is at a pressure of 0.5 atmospheres, nitrogen is at a pressure of 0.7 atmospheres, and carbon dioxide has a pressure of 1.2 atmospheres. Calculate the total pressure inside the tank. Okay, so if I'm looking for total pressure and it gives me all these partial pressures, I'm going to use Dalton's law up here. So I'm going to go ahead and list out what it gives me. First of all, it says that my tank here is at 25 degrees C. That's just there to throw you off. If you're finding total pressure from partial pressures like this, you do not need the temperature. So that's just there to throw you off. Okay, but it says my oxygen has a pressure of 0.5 atmospheres, so that's my P1. One of my partial pressures is 0.5 atmospheres. My second gas has a pressure of 0.7 atmospheres, so we'll call him P2, is 0.7 atmospheres. And my third gas, carbon dioxide, has a pressure of 1.2 atmospheres. So that's my P3, 1.2 atmospheres. And we want to know, based on that, what's the total pressure. So total pressure is PT, that's what we want to know. All we have to do then is add it up, because the total pressure is always going to be equal to the sum of the partial pressures. Easy peasy. So my total pressure then is going to be 0.5 atmospheres plus 0.7 atmospheres plus 1.2 atmospheres. That's it. You just add them together. So when you add those together, you should get a total pressure of 2.4 atmospheres total. Okay, the next question says the total pressure inside a 40-liter tank is 17 atmospheres. Inside the tank are 3 gases, oxygen, nitrogen, and carbon dioxide. Oxygen's pressure is 4 atmospheres, nitrogen is 11 atmospheres. Calculate the pressure of carbon dioxide. So this one's a little different because they're giving you the total pressure here, and they're asking for one of the partial pressures. So first step is the same though, list what they give you. So I see that they give me here the total pressure is 17 atmospheres. So my PT is 17 atmospheres. It says one of my gases, oxygen, has a pressure of 4 atmospheres. So we're going to call that my P1 is 4 atmospheres. It tells us that nitrogen, one of my other gases, has a pressure of 11 atmospheres. So P2 is 11 atmospheres. We want to know what the pressure of the third gas is. So P3 is my unknown here. We're going to set it up the same way though. So pressure equals P1 plus P2 plus P3. And you can go on, if there's 4 gases, you just do plus P4 plus P5 plus P6, however many gases you have. So let's plug it in. My total is 17 atmospheres on the left. P1 is 4 atmospheres. P2 is 11 atmospheres. And P3 is what I'm solving for. So for me, the first step I would do here is just combine. 11 plus 4 is 15. So if we rewrite that, 17 atmospheres equals 15 atmospheres plus my P3. Then all you have to do to isolate P3 and solve is subtract 15 atmospheres from both sides. That gets rid of it here. So then we get that P3 is equal to 17 minus 15, which is just 2 atmospheres. Okay, again, if you have any questions on this, email me, send me something on Remind, talk to me during office hours, but go through your to-do list and check through all the assignments as you go. I hope you all have a great week, and I will talk to you next week.